Welcome to Fun Facts Online. Our planet is wrapped in an invisible shield, a magnetic field that protects us from the harsh radiation of space. This shield is powered by a giant engine deep within the Earth, an engine with a solid core. But for decades, scientists faced a baffling paradox. According to our best understanding of physics, that solid core should NT have been able to form in the first place. The engine that protects us all should NT exist. Today, we're diving into the heart of our planet to uncover the surprising solution to this mystery, and it involves an element you might not expect to find there: carbon. To understand this puzzle, we first need to take a quick journey to the center of the Earth, a place of almost unimaginable conditions. Our planet is built in layers, like a giant geological onion. We live on the crust, a paper-thin skin of rock. Beneath that is the mantle, a vast layer of hot, slowly flowing rock that makes up most of Earth's volume. But the real action happens deeper, still, in the core. At a depth of about 900 kilometers, we reach the outer core. This is a colossal ocean of liquid metal, mostly iron and nickel, swirling at temperatures over 4,000 degrees Celsius. It's the ceaseless churning motion of this metallic sea that generates Earth's magnetic field. This is what scientists call the geodynamo theory. Think of it like a giant, self-sustaining electrical generator. The movement of the electrically conductive molten iron creates powerful electrical currents, and these currents generate the magnetic field that extends far out into space, creating our protective magnetosphere. But at the very center of our planet, about 150 kilometers down, things change. Here lies the inner core. It's a solid ball of iron and nickel, roughly the size of Pluto. Even though it's as hot as the surface of the Sun, the immense pressure at the center of the Earth, over 3.6 million times the pressure at sea level, is so great that it forces the metal into a solid state. The existence of this solid inner core is absolutely critical. The geodynamo isn't just powered by random sloshing. It's driven by a very specific process, the slow growth of the solid inner core. As the whole planet gradually cools over billions of years, iron from the liquid outer core crystallizes onto the surface of the solid inner core. This freezing process releases both heat and lighter elements into the remaining liquid of the outer core. This hotter, lighter, less dense liquid then rises, creating powerful convection currents. It's this convection, this constant churning, driven by the freezing of the inner core, that powers the geodynamo and sustains our magnetic shield. Without a solid inner core that is actively growing, our magnetic field would eventually die out. And this brings us to the great scientific conundrum, the inner core nucleation paradox. For a liquid to turn into a solid, it either needs a tiny seed particle to start crystallizing around, or it has to be supercooled, that is, cooled to a temperature well below its actual freezing point. Think of very pure water in a smooth glass. You can sometimes cool it below 0 Celsius, and it will remain liquid until you disturb it, at which point it flashes into ice. Scientists calculated that for a core of pure iron and nickel to start freezing on its own, it would have needed to supercool by a staggering amount, somewhere between 800 and 1,000 degrees Celsius. This presented a huge problem. If the core had supercooled to that extent, the moment it finally started to freeze, it would have been a rapid, catastrophic event. The inner core would have grown massively and quickly, completely changing the dynamics of the core and likely causing the Earth's magnetic field to fail spectacularly in the distant past. But we know this didn't happen. By studying ancient rocks that have recorded the direction of the magnetic field at the time they formed, we know that the Earth has had a stable, continuous magnetic field for at least 3.5 billion years. There's no evidence of a catastrophic failure. The engine didn't suddenly stop and restart. So how did the inner core begin to form so gently without this impossible degree of supercooling? For years, this was one of the biggest unanswered questions in geophysics. The answer, it turns out, was hidden in the core's chemical makeup. Recent research, published in 2025, has provided a compelling solution. A team of scientists used powerful computer simulations to model the conditions at the center of the Earth. They knew the core wasn't just pure iron and nickel. It also contained small amounts of lighter elements that dissolved into it during Earth's formation. They decided to test how these elements, specifically silicon, sulfur, oxygen, and carbon, would affect the freezing point of iron under core pressures. Their findings were a major surprise. They found that some of the elements they expected to help, like silicon and sulfur, actually made the problem worse. They inhibited freezing, meaning even more supercooling would be required. But one element did the exact opposite: carbon. The simulations showed that carbon dramatically accelerates the freezing process. The researchers ran the numbers with different amounts of carbon. With about 2.4% carbon mixed into the iron, the required supercooling was still too high, around 420 degrees. But when they increased the carbon concentration to 3.8% of the core's mass, the required supercooling dropped to a much more plausible 266 degrees. This was the breakthrough. A supercooling of 266 degrees is something that could have realistically happened in the Earth's history, allowing the inner core to begin forming spontaneously but gently, without the catastrophic flash freeze scenario. This specific carbon-rich composition is currently the only known recipe that can explain both how the inner core started to form and its currently observed size. It seems that carbon, the very basis of life on the surface, is also the secret architect of our planet's deep interior. This discovery elegantly connects the dots. Carbon's role is twofold. First, it acted as the crucial catalyst that allowed the solid inner core to nucleate, to begin existing in the first place, solving that long-standing paradox. But its job isn't done. The ongoing process of this iron-carbon alloy crystallizing onto the inner core is what continuously fuels the geodynamo today. As the iron and carbon freeze into a solid, the remaining liquid in the outer core becomes enriched in other, even lighter elements. This less dense liquid becomes buoyant and rises, stirring the entire molten ocean of the outer core and driving the convection that powers our magnetic field. So carbon didn't just kickstart the engine. It's a key part of the fuel that keeps it running over geological timescales. The importance of this carbon-forged shield is impossible to overstate. This magnetosphere acts as our planet's first line of defense, deflecting the solar wind, a constant stream of charged particles flowing from the sun. Without it, that solar wind would strip away our atmosphere over time, boiling off our oceans and leaving Earth a barren rock, much like Mars is today. It also shields us from high-energy cosmic rays and the violent particle bursts from solar storms, which can harm life and fry our delicate technological infrastructure. The story doesn't end there, though. Our magnetic shield is a dynamic, evolving entity. There are areas where it's weaker, most notably the South Atlantic Anomaly, a vast region stretching over South America and the southern Atlantic Ocean. Here, the magnetic field is significantly diminished, allowing space radiation to dip closer to the surface. This dent in our magnetic armor poses a risk to satellites passing through it, and it appears to be growing and shifting, reminding us that the geodynamo deep below is a living, breathing system. The exact composition of the core is still a hot topic of debate. While this research points to carbon's critical role, other studies suggest elements like silicon, oxygen, and sulfur are also needed to explain the core's precise density. And the exact age of the inner core is another mystery, with estimates ranging from 500 million to over 2 billion years old. The new evidence about carbon's role will help scientists refine these models and get closer to a definitive answer. Ultimately, the story of carbon in Earth's core is a powerful testament to the incredible and often hidden connections that make our planet habitable. An element we associate with trees, animals, and ourselves, is also the linchpin for a colossal geological process happening thousands of kilometers beneath our feet. The formation of our solid inner core, facilitated by a specific amount of carbon, was the crucial step in forging the magnetic shield that has protected our world for eons, allowing it to become the vibrant, living planet we call home. The journey to the center of the Earth has revealed that our planet's habitability is written in the language of geology, and carbon is one of its most essential words. Thanks for listening to Fun Facts Online.